Alrighty, welcome back. Now we're going to look at number 4 in chapter 6. This was another tricky one. I don't understand why they only made it 1 dot. Number 3 and number 4 are definitely harder than 1 dot. Number 4, a child goes down a playground slide with an acceleration of 1.26 meters per second squared. Find the coefficient of kinetic friction between the child and the slide if the slide is inclined at an angle of 33.0 degrees below the horizontal. Alright, fine. We have an incline. We have a child, which coincidentally looks like a box. We have an angle here, an angle theta, which happens to be equal to 33, it's supposed to be 3.0 degrees below the horizontal, above the horizontal. Depends on which way you're looking. If you're looking down here, it's below the horizontal. If you're looking up from the bottom, it's above the horizontal. Don't really care. It's 33 degrees. Now, they would like to know what the coefficient of kinetic friction is. That's the thing that we want. We do know that she accelerates downward, and you can tell it's a girl from the shapes. Okay. Our acceleration is downslope at a rate of 1.26 meters per second squared. If I can get that to look like a squared. All right. And of course, because that's the direction of acceleration, we are going to call that the x-axis. X is downslope, so my acceleration is nice and positive. Y is perpendicular to it. Why not? Now, we have our forces here. We have our weight in the downward direction. We have our component of weight, which is in the y direction, which is perpendicular to our slope. We have our component of weight going in the downslope direction, which is w sub x. Our angle, due to symmetry, goes up here. That is the same angle as this one down here. I'm not going to squeeze 33 degrees in there. Now we know in the y direction nothing's happening. It's boring there. So the size of my weight in the y direction is the size of my normal force. So I should draw it about the same size. My normal force, and I'm going to mention it here, happens to be equal to my weight in the y direction, in magnitude, not direction. And of course, they want a coefficient of kinetic friction. That means there is friction, and that frictional force is upslope. It is in the negative x direction. That is my frictional force. And if I want to get nitpicky about it, it's a kinetic force, F sub k. All right. Now we can get down to the nitty-gritty here. We're going to explore everything that we can about the acceleration. We've got to use this number and this angle here in order to find this coefficient. So what we're going to start with is we're going to start off with a statement for acceleration. Acceleration is equal to our net force divided by our mass. Our net force in the x direction, that's the direction where acceleration is occurring, is a negative force. We have two forces in the x direction. We have the weight in the downward direction. We have the frictional force in the upward direction. Upslope, downslope. Shouldn't say up and down. Now, of course, the weight in the x direction is bigger than the frictional force. Otherwise, it wouldn't be accelerating that rate. So I'm going to say that my weight is positive, and I'm going to already assign my friction being negative minus the frictional force, F sub k, divided by my mass. Should have started over here. I really don't have enough room here. Now, my weight in the x direction is equal to my weight, which was mass times gravity. And it's the opposite side from this angle, so that's going to be sine SOHCAHTOA, so that's the sine of my angle. My weight in the y direction, which is coincidentally equal to my normal force, is therefore going to be equal to the mass times gravity times the cosine of theta. All right, we're going to make a substitution for both of those guys up here. So my acceleration is equal to the weight in the x direction, that is mass times gravity times sine of theta, minus my frictional force, which is of course we know frictional forces are mu sub k times the normal force, but we know the normal force is W sub y, which is equal to this. So that means I'm going to subtract, that's the subtraction there, my mu sub k, my coefficient of kinetic friction, times my normal force, which is equal to my weight in the y direction, the component in the y direction, which is this guy. Mass times gravity times the cosine of theta. And of course that whole thing is divided by mass, which that's kind of nice because mass cancels out. That's what we see a lot of. And so we get a statement here that acceleration is equal to g times the sine of an angle minus mu sub k times g times the cosine of the angle. And so we can rearrange a few things here. We can subtract this out. Actually, I'm going to add that to the other side and subtract my acceleration over to this side. So I'm going to end up with a formula that mu sub k is equal to, that goes to the other side, so I'm going to get g sine theta minus the acceleration divided by g cosine theta. Now, I'm not going to bother reducing this one, but we should already see that if I didn't have this acceleration over here, if this thing was sliding down at a constant velocity, my g's would cancel out and I'd have sine over cosine, which is of course just equal to the tangent of theta. When something slides down a ramp without accelerating and all the forces are in balance, it's very simple to find the coefficient of kinetic friction. When it does accelerate, you get a slightly uglier formula. Alright, so we've got 9.81 meters per second squared. I'm putting in magnitudes. I'm not worrying about positives and negatives right now. I already dealt with my positives and negatives up here. I already assigned everything negative when I wanted it to be negative, positive when I wanted it to be positive. 9.81 meters per second squared times the sine of 33.0 degrees minus my acceleration of 1.26 meters per second squared divided by, again, 9.81 meters per second squared, this time multiplied by the cosine of 33.0 degrees. And it does make me feel better to do that. Alright, fine. Almost got an answer here. Mu sub k, let's see, 9.81 times the sine of 33. Sine of 33 is 0.54 something. Multiplying that by 9.81, I've got 5.34. I'm going to subtract off my 1.26. That's going to give me in my numerator 4.08. And I'm going to divide that by 9.81 times my cosine of 33 degrees. Cosine of 33 degrees is 0.84. So that makes my numerator, my denominator 8.2 something. And so I end up with a coefficient of friction, which is in a reasonable range, which is equal to and I guess I do get 3 sig figs here, 0.496. That is my coefficient of kinetic friction as it goes sliding down. In other words, if I was on a flat surface, I would have to push the girl with based on the material that she's wearing and the material that the slide's made out of. I would have to push her with a horizontal force, which was 49.6% of her weight, to get her to move at a constant rate. That's another way of looking at it, and that's really what coefficient of kinetic friction means. Sorry that this one took almost 10 minutes.